We're in 3.9 related rates. Example 3 is a candy company makes a thin-shelled waffle cone filled with chocolate. The cone is 20 millimeters high with a base radius of 5 millimeters. Liquid chocolate fills the cone 3 millimeters cubed per second, shown in the orientation below. When the chocolate is 2 millimeters high, how fast is the chocolate height changing? So this is one we're given in a schematic, and that would definitely be expectation here for a problem like this because it's got a lot of details, and so we're given a setup, which is kind of nice. So let's get going, and I'm actually going to start working on the solution over here so we can have that picture in our sights for as long as possible. Okay, so what are we trying to find? And so we're just going to look at what was being asked. When the chocolate is 2 millimeters high, how fast is the chocolate height changing? So be careful here. Every single one of these problems is asking for a rate, which is going to be a derivative that we're going to write in Leibniz notation. So how fast is a rate, meaning that it's a derivative with respect to time, and it's of the chocolate height changing, and so that means that we're looking for dH over dt. And then a little weird, but we write when and then a dimension that's given. Chocolate is 2 millimeters high. So when h is 2 millimeters. So let's at some point take a look at the picture and picture it in motion here. We have some chocolate that's coming in here, and then it's filling the cone, and so that chocolate is what's shown on the inside of the cone, and that height is increasing, and the dimensions of the waffle cone are remaining the same, and so they're given the constants of 5 and 20, and we don't really need a variable for that because they are constants, they don't change with time. And so the radius is changing and the height is changing of the chocolate on the inside, so you can picture that chocolate filling and try not to get too hungry. So now we'll start writing down some things that are given or known, and it's not like you have to write everything down. There's a lot of information in the picture, but a biggie is that you need to have the rate identified. And we were given a rate of 3 millimeters cubed per second. Again, the units are not something you're going to have to worry about in terms of converting units, but they help you identify what the rate is. So it's per second, which makes it a rate. And we have a length cubed, which is volume. So we know that that rate that was given is dV over dt. You can tell by other ways too, but I think the units are probably one of the most obvious ways. So, alright, so we have that, and some other given in the picture. So I think we're ready to get started on our equation, or equations. So a couple different ways to think about this. It must have, these equations or equation must have the rate that you're looking for stripped down of its rate part and the variable that remains. So it must have the volume because that was given as a rate. So the formula we're going to have, or equation, has to have V in it for sure. Other things, we were trying to find dH over dt. So if you take the rate part off of that, then we need to have an equation with h in it. Oops, I don't know what I just did there. Hold on. So must have a V and an H, and maybe some other stuff. So with all the examples I've been doing, the volume's been involved, and that's not going to be true of absolutely every example, but so the equation here to start out with is more obvious than it can be at times. So let's write out that volume equation for a cone. It's 1/3 pi r squared h. So we see that we have an h in here and a v, so that's good. But we also have an r. And as we identified in the beginning of the problem, r changes with time too. So it's a variable with respect to time, as is volume, as is h. So when I take this derivative with respect to time, what would happen automatically is I would get a rate for the volume, a rate for the r, and a rate for the h automatically because they change with time. But I don't have a rate for the radius. I don't have a dr over dt. It's not there, it's not given. And so that's a problem because I won't be able to plug in that value. And so that is the time that you should think about, well, is there some given information I haven't used? How can I write another equation or a constraint that is going to help me boil down this overall volume equation into something that doesn't have an r? So a lot of ways we could summarize that. Need to get rid of the r with another equation. And I'll just put in parentheses here that dr over dt is not given. Okay, we'll just leave it at that. And so notice that the dimensions of the cone haven't been used. The fact that it's 5 by 20 millimeters, and definitely that's going to have a play in the answer because the rate of change of the height is going to depend on how big this waffle cone is, so it's definitely something that's needed here. So in search for this other equation, now I want to relate, maybe I'll label this here as a second equation. What we need is r and h in it. And this is so we can write the volume equation as a function of just h, not just a function of h and r, something like that. Well, let's write another or draw another picture here that is just going to highlight a little bit more of what's going on with r and h as it relates to the dimensions of the cone. So notice in the cross-section view we have a right triangle with the overall radius being 5. So here's the cone in dots. And then we have our overall height is 20. And then the chocolate height is and radius are changing. And I just realized I should be a little bit more careful about this 20. I'll put it out here. Okay, so that's what we have going on. And so how can we relate these in the equation? Well, you might notice that we do have similar triangles here. And so we can set up a proportion that relates r and h and the given and the constraints of the dimensions of the cone. So what I like to do is set up the proportion, which is two fractions equal to each other, And then I'm going to start with r, which means that the 5 is the corresponding edge. Either has to go below it or on the top of the other side. So I just chose to do it there. And then the rest of this is force r. What it has in common with the height is that it's in the same triangle with h, and then the corresponding edge to h is 20. And so, and 5 and 20 can be across from each other because they're part of the same triangle. So there's different proportions you can set up. Some wrong ways to do it, but most of them are right. This one is correct. So now we're going to solve this little equation for what you have to decide. So looking at the equation again, this is something students really get confused with. So remember, you're trying to get rid of the r in there. So what we're going to do is we're going to solve for r so we can plug in terms of h for the r, and that gets rid of the r from the volume equation. So that's a piece of cake. We just multiply both sides by 5 and we get h over 4. So now we're going to sub in. So we're going to put h over 4 in here, and you get 1/3 pi h over 4 in parentheses squared times h. Simplify. 1/3 pi h squared over 4 times 4 is 16 times h. Keep going here. We're going to get pi over 3 times 16 is 48, and then h cubed. So we're almost done. We're on the derivative step. Notice how much work we had to do before the derivative step. So it's hard to be forward thinking on this in the beginning, and it's something you'll get more accustomed to. It's tempting to get that derivative step, kind of go on to that stage, but you want to make sure you're absolutely ready as best you can be, or you're going to run into problems. Okay, so this derivative is actually pretty easy now. It's dv over dt is equal to pi over 48, and then we take the derivative of h cubed. H depends on t, and so we use the chain rule here, take the derivative of the outer function, evaluated the inner function, which is 3h squared, and then the derivative of h, the inner function, is dh over dt. Now we're on the sub and solve step, and let's see what we have. Well, dv over dt was given. We had that as, what was it again, 3. And then dh dt is what we're looking for, so it's good we don't know that. What's h? We're supposed to do this when h equals 2. So this was a pretty straightforward, and this one we can just go ahead and plug in here and see what we get. Three times 2 squared, and then we have our times dh over dt. So we just go ahead and finish this. Basically divide by all this stuff. We're going to have the 3's go away. We're going to have 48 on top. And then we're going to have pi and 4. Divide that in there, and we get 12 over pi, exactly. So that's great. You can leave the answer that way. But remember, for these word problems, if you'd prefer just to write the decimal answer, that's fine.